This video, we are going to begin our discussion over section 12.5 over something called the TNB frame, curvature, and torsion. So where I want to begin with this TNB frame thing, to explain it, it comes from a couple French mathematicians or physicists. I'm actually not sure of their background. What I want you to do is imagine that you are watching a plane fly out towards a horizon, right? And you can see it's let's say it's a stunt plane. It's doing a bunch of flips. And you're looking at it, and the way we're looking at it from afar, we see one perspective, the plane flying around. There is another perspective to the story, though. If we were sitting inside the plane, riding around in the stunt plane, right, flying around in the air, our perspective would be changing every second that we're flying, and it would be going all over the place. What this TNB frame thing captures is it actually captures which way the plane is flying, turning, and twisting. The first thing we're going to deal with is talking about where the plane is heading. This is based on our tangent vector. This makes sense. Our tangent, if we had a point here, right, the tangent tells us the direction of our particle. Nothing new there. The way to think about it for this type of problem is that the nose of the airplane is pointing. That is the tangent vector. It's pointing in the direction that the plane is flying. That is the nose of the plane. The next thing we have is called the normal. And I put this like T like that because that's how we note it, is we put T with an arrow and N with an arrow. These are unit vectors. Even though we don't put the hat over the vector, it's still a unit vector. Binormal, or actually we didn't finish talking about normal. Normal is the, it's coming out the side. It's where we're thinking the tail fin that's here is sticking out. So it does make a 90-degree angle with our tangent vector. This tells us where it's pointing. This makes sense. If I have a two-dimensional curve like this, here's my tangent vector, and here is my normal vector. Well, the curve is turning to the left, so it's pointing to the left. It tells us which way it's turning. Now, that's at 90 degrees, and then we also have this like coming up here that's 90 degrees with both angles there, making like a corner of a box. This third vector shooting straight out, being the wings, is called the binormal. This actually affects how the plane is twisting. If you think about how a plane flies in space, right? If you've ever flown a plane in a video game with multiple sticks or anything like that, it's not the same as a car. There's much more twisting going on. Anyway, what these vectors are, the best way to think about it is if we take a look at our picture here, it's like this is being my tangent. It's like the corner of a box flying around. So this is the tangent. That's the beginning of the plane sticking out, right? The nose of the plane. And that box would be flying along this curve. And the vectors would be changing every second. Every time we move, the vector would be changing unless we were flying in a straight line. These vectors are all mutually orthogonal. We mentioned that they all make a 90-degree angle with it. They're just like I, J, and K. We do have formulas for this. This first one is not a surprise. It's the tangent vector. So if I take the normal tangent vector and divide by its magnitude, I get a unit tangent vector. No surprise there. Now, if we think about a normal vector with that tangent vector makes a 90-degree angle, it would make sense to think about the derivative of the tangent vector. The tangent vector of the tangent vector is called a normal vector, right? These two vectors are orthogonal, meaning they meet at a 90-degree angle. They do divide by the magnitude there to make it a unit vector. These two vectors, T and N, sit at a 90-degree angle, and then the B vector pokes out at a 90-degree angle from those. It's orthogonal to both. So if we need a vector that is orthogonal to two vectors, we have learned in chapter 11 that we just take the cross product of those two vectors. If we find the cross product of those two vectors, I get a vector that is orthogonal to both. That is the important part of the cross product, being orthogonal, the result is. So that is a TNB. It's pretty neat, I believe. I like them. It's kind of cool seeing how the vectors change. I do want to show you a picture of this to help. I have a GIF or GIF. I don't know the way to pronounce it. The T being the tangent vector, in the blue being the normal vector, and the green being the binormal vector. So as you can tell, the red vector points to where the particle, the meeting of those three vectors there, is moving. The red points, the blue is pointing to the left, and you can see that our particle is turning to the left, and then the green vector is kind of leaning back, so it causes it to go up. Hopefully you can see how these could be helpful for us. It could be a roller coaster, it could be anything like that. Car, just talking about a perspective of something moving through three-dimensional space. All right, we're going to talk about a few things here to kind of extend on this. Why do we care, right? So a measure, first thing we're going to do here, applying this kind of stuff, is we're going to talk about curvature. A curvature is a measure of a curve's failure to be aligned. So if I had maybe some kind of shape like this, the more curvy the function, the larger the curvature. So over here, it would have a small curvature. But over here, it would have a very large curvature because it's more curvy. A way to think about this, and I would like you to stop and really think about what this is saying. Curvature is really arc lengths compared to heading. Right? Think about arc length is how far we're going to travel. Heading is how much does it change. How much, heading being like how much does the plane change. Like this is the unit tangent vector goes from here to here. It's like changing quite a bit, right? But over here, the unit tangent vector probably is the same. So that's what they mean by heading, is that tangent vector changes. If it changes a lot compared to a big arc length, that tells us something. All right, so the larger the number, when we do that, the larger the curvature, right? The more it's curvier it is. Wow, I am failing with my English there, so I'll stop. So let's deal with kappa. That is our curvature. This is how fast is the tangent changing when compared to s, which is arc length. Or we could write it this way, t prime of s. Now we're going to work through this to get some other results here because that formula is fine, but we'd have to find arc length every single time. So I'm going to rewrite this derivative. We have big T, the change in big T over little t, and then we're going to use something here. It's like a chain rule. It's not that they cancel, but it looks like they cancel. You talk about this in Calc 1 and 2, but we can write it like that, right? If I write it like this, now I can solve for dt ds, right? If I do that, I get dt dt divided by ds dt. Right? I take the magnitude of all three sides. Remember, we're trying to find a cleaner formula. That's where we're headed. Maybe something that doesn't require arc length. So I'm just taking the magnitude of everything. Right? And then we're going to make some replacements here. All right, we get k, that's what that is on the left, equals, and then we're going to have a formula here. Up top, we can just write it the way it is. Tangent vector, the derivative of it, take the magnitude. And then the bottom, let's think about that for a minute. Let's start with this definition of arc length function. We have from A to B of R vector. Right, this was arc length. Right, now if I take the derivative of each side, all right, then we have the derivative of an integral. All right, and those are inverse operations, so they undo each other. So this gets us ds dt is r prime. All right, so we can replace that below with the tangent vector. All right, there we go. So that's where that replacement comes from. So now we have a new definition for curvature. So let's write that down. Curvature, or that's how curvy the curve is the tangent vector, the derivative of that, take its magnitude and divide by the magnitude of r prime. There's one definition. I have another formula. I'm not going to show you where it comes from. I'm just going to give it to you. If it's a polynomial, and you only need curvature, then use this. So here's this definition. And you'll see why I would only use it if they're polynomials. So let's write it down first. The r prime, the cross product with r prime with r double prime, and then we take the magnitude of that vector, and we're going to divide it by the magnitude of r cubed. So you can tell, I think, why, hopefully you can see that, why we would only use one of polynomial, because we have to do a first and second derivative, then we'd have to cross it. Polynomials, things go away really quick. We end up with a lot of zeros, stuff like that. It's easy to take derivatives of polynomials and then cross them. So if that's a polynomial, if you're dealing your r function, right, your vector value function is a polynomial, we would want to use that formula. All right, one last idea. This is called torsion. There is a crazy formula up there that will work for torsion. I'm not going to talk about where that comes from. With torsion, what torsion is it's a measure of a curve's failure to be contained in a plane. What I think about when I think of torsion is I think of a roller coaster that's on one loop, that is going repeatedly in one loop, and torsion would be the measure of how much that roller coaster wants to leave the loop. Or you can think of like, okay, if I had a loop, it would just, if it were staying in the same place, it would just do this, right? But if I had a loop that was failing for that, it would like come off, right? You can think about this in 3 dimensions. It's staying out of that single plane. If it stayed in the loop, it would stay in a plane. I'm not going to really talk about where this comes from. It's a dot product of your binormal with respect to arc length, negative dot with the normal vector. We're not going to talk about where it comes from. Not going to expect anything from you on that. But that's where you find torsion. We do need to talk about another idea called the osculating circle. The osculating circle is going to make this make a little more math sense. So this circle, at any point on a curve, so you pick your curve, you pick a point, there will be a circle that fits that curve best. What we mean by best is that it just touches the curve, just barely, like a tangent. The circle and the curve both have the same tangent, they have same curvature, and the same normal points through the center of the circle. So what that means is they both have that same tangent here, right? They have the same normal, but the normal goes through the center. So like the circle doesn't have a normal, the curve would have a normal there, and it would run through that center. They also have the same curvature. All right, this is called an osculating circle. The way I think about this osculating circle, I think this helps us understand the idea of the plane when it comes to torsion. Is that circle is almost contained in a plane. It is contained in a plane. Getting out of that plane would define our torsion. So this is called the osculating circle. A couple things with that, we can kind of see it here. The osculating plane contains the circle, and it also contains T and N. You can see that picture here, that T and N is in the same two-dimensional plane as that circle. B would be sticking out right at us or sticking inside. That is our normal to this osculating plane, sticking out. The radius of osculating circle is called the radius of curvature. How we find that is once we have kappa, which is the curvature, 1 divided by that measurement gives us rho. Unfortunately, rho is going to play another part. I think we've used it in polar, in Calc too, but we're going to use it later this semester for something else as well. Okay, so the plane that contains N and B, that's the one sticking at us, and N vector is called the normal plane and contains all vectors orthogonal to the tangent vector. Here is just an introduction to all this. We'll do a few problems of finding T, N, and B, curvature, the osculating plane, all that kind of stuff. But that's about as far as we'll take it, is discussing what it is. You guys are going to chew on it with some exercises, and then we're going to leave it behind. Really cool idea.